Hello students, welcome back to another session of Power Hour live lecture series for NEET 2025 and continuing on with another topic of physics for your modern physics basically is dual nature of matter and radiation. Let's continue. As we know कि for light we have a perception that it shows or it portrays dual nature. Dual nature means sometimes it shows, or in some phenomena it shows wave nature, as well as in some phenomena it shows photoelectric effect like particle nature. So particle nature and wave nature at different times we can easily analyze, but the thing is ki in classical mechanics we can explain most of the phenomena using particle nature, but as far as the modern physics is concerned, we need to analyze both of them. Okay. So for this, to verify the wave nature of light, we have two phenomena in front of us. One is your interference. Interference is waves. Interference in case of waves, we can see when alternate pattern of constructive and destructive interferences, the bright and the dark fringes are obtained on the screen, as well as in the single slit diffraction or in the single slit scenario we observe the diffraction pattern just like interference pattern, which shows us the wave nature of the light. Okay. Now moving on to the photon theory, we know that light constitutes of photons, which are basically the energy packets or the particles of light. What are the different aspects of photons? So as per Max Planck's photon theory of light, basically photon electromagnetic radiation is in the form of wave packets or quanta, which are classified as photons, which are known as photons, the quantum of energy. The photon has definite energy and momentum properties of photons. Firstly, we should know key electromagnetic waves, they all travel at the same speed, that is the speed of light in a particular medium. In vacuum, the speed of light will be 3 into 10 to the power 8 meter per second approximately, and in some another medium it will be something else like that. So all the electromagnetic radiations travel at the speed of light. So all the photons travel at the speed of light. Okay. Now for the energy of the photon, we must remember the formula for the energy of photon. In the energy of photon, I can write hc by lambda or h nu, which is basically hf. F is the frequency, nu is the frequency. Here h is your Planck's constant, 6.63 into 10 to the power minus 34 joule second. C is your speed of light, 3 into 10 to the power 8 meter per second. Lambda is the wavelength and nu is the frequency, or you can write it as F. If I write this thing, the energy of photon hc by lambda, everything in SI units, so energy comes out to be in joules. But if I want to get the energy in electron volts, then I have another formula, 12400. It's an approximate formula where this lambda should be in angstroms. Then I get the energy in electron volts. Generally we are going to use this, to energy in electron volts, like this. So we need to remember this formula, and most important thing is whenever the lambda is given in angstrom, you can directly opt for this formula to get the answer in electron volts. Okay. The momentum of the photon. So we'll later on see the de Broglie's hypothesis based upon the same concept, the momentum of the photon. We say that the momentum of the photon is energy upon the speed, and it comes out to be h by lambda. Okay. What is h? H is your Planck's constant. And what is lambda? Lambda is the wavelength of that photon. So h by lambda is the momentum of a photon Some properties and some points regarding the photon is rest mass of photon is considered as 0. Energy and the momentum of a photon, they always must be conserved. The number of photons may not be conserved because with time more and more photons can come and fall on the surface. Okay. This particular point is important from the aspect of photoelectric effect. Basically, what does it say? A particle or a substance can absorb a photon, okay, can absorb a photon and take up its energy. Also, an excited atom can go from one state to another, generally lower energy state, lower energy level, and it can emit energy in the form of photons. So, you know all the emission spectrum of your atom in your Bohr's atomic model, in your atomic structure. You have studied it twice, once in physics as well as once in chemistry. So there also, in the transition from higher energy level to lower energy level, we are going to see emission of photons corresponding to that energy difference. Okay. Let's move on to the next part, intensity of light. So intensity of light you need to understand in the terms of energy falling per unit time per unit area in the form of photons. Only the photons we are discussing here, so photons are falling per unit time per unit area. So let's talk about this. Intensity of light is defined as the energy crossing per unit area per unit time. Remember that point first of all. Energy per unit time per unit area perpendicular to the direction of propagation. Correct. The intensity of light is associated with the number of photons. Again, it's important point. The intensity is directly proportional to the number of photons, and it's also proportional to the energy of the photons. Like this. The wavelength and the frequency of light associated with the energy of the photons, if it increases, then wavelength frequency increases, wavelength increases, wavelength decreases, and the energy of the photon increases. That we all know. It's directly written from the formula E is equals to hc by lambda and E is equals to hf, where f is your frequency or nu. Okay. So here you can easily see frequency increases, energy must increase, and wavelength decreases, so again energy must increase. Here they are showing a particular aspect of a point source of light. Let's say point source of light is going to emit several spherical wavefronts, and they are considering some cross sections in the direction of propagation and different cross sections like this. So if you see, as we go further and further, the area of cross section is going to increase. So I can definitely say intensity was energy per unit area. So intensity is going to decrease. Okay. Next thing, the photon count, the number of photons emitted per second or per unit time, small n. Photon count. Okay. Okay. The power P of the source is given to us. That means ki suppose there is a light source which is emitting energy per unit time in form of power P. It is nothing but simply energy per unit time. And the wavelength of the photon is given as lambda. Energy associated with one single photon is hc by lambda. We all know this. Now they are saying ki if n is the number of photons emitted per second, then how can I get the power? So basically I can write power as total energy falling per unit time, and in the total energy I'll take total number of photons and their energy falling per unit time. So number of photons per unit time is small n and the energy is E. So this is how I can write the power here. So you can look here, the power is number of photons per unit time. So the power should have per unit time factor, and this small n takes count of that. Okay. Alright, from here they have written another formula. If I can just write this thing, so n is equals to hc by lambda. We'll correct this thing. P equals n times hc by lambda, okay. Now they are asking number of photons. If we know the power and if we know the energy, just cross multiply. So this gives me n is equals to the power into the wavelength upon hc. Okay. So here the n will be equals to power into wavelength upon hc. So if the question asks find out the number of photons falling per unit time or number of photons carried in a wave per unit time emitted by a source per unit time, then I can just write the power the power of the source and the energy of the photon, and that gives me the answer. Straightforward. Okay, they are asking about photon flux. So just now we saw number of photons falling per unit time, the photon count. Now I want to talk about photon flux. You guys have an idea about the flux? What is flux? It is something telling us about the flow of some quantity, whether it's electric field, magnetic field, or in fluids we see the flow of liquid, the flow of the fluid, just like here the photon flux. They are saying that photon flux is defined as number of photons incident normally on a surface per second per unit area. So there we saw small n was the number of photons per unit time. If I divide it with the area, I get photon flux. So here I'll write the photon flux as phi, and it will be small n number of photons per unit time divided by the area over which it is falling normally to the surface. Okay. So small n is written as the power upon energy, and in the denominator one more area A. And further I can write different formulas of energy and I'll get the photon flux. So again NEET has asked direct questions based upon photon flux. So we must remember this formula, this concept. Alright, here the P represents the power of the source. Absolutely right. The energy incident on the surface per unit time, that's the power of the source. And the power upon area will be written as the intensity. We know this thing, intensity. And if I can write intensity as I, so power upon area is I. And here the photon flux comes out to be then I upon the energy. So if I have the intensity and if I have the energy of a photon, then I can easily get photon flux. Intensity of the radiation, energy of a photon, energy of the photon. That's how we can get photon flux. Okay. Now let's talk about different types of emission, electron emission, for which we are going to discuss the photoelectric emission soon enough. Okay. So electron emission, basically I need to understand ki how an electron gets emitted from the surface, what are the requirements, and what are the possible methods with which we can do electron emission. So one aspect they are mentioning for us in the starting itself is there must be some minimum amount of energy required by the photons, because photons are responsible for ejecting out or emitting the electrons. So that minimum amount of energy must be required so that we can remove an electron from the metal surface, and this minimum energy is called work function of the metal. Work function of the metal. The work function phi depends upon the nature of the metal surface. The phenomena of emission of electrons from the surface is called electron emission. Okay. Different types of emissions. First one they have mentioned is thermionic emission, that means due to the heat. So we can say by suitably heating the metal surface, sufficient thermal energy can be imparted to the free electrons from the surface of the metal, so that they can be ejected out from the metal. They can come out of the metal. Field emission. Field emission is basically applying a very strong electric field on the electrons so that they get energized. If we apply the field, they get energized, and with that energy they can easily eject out of the metal surface. They have given the order of the required electric field. The required field to eject out electrons is 10 to the power 8 volts per meter or Newton per coulomb. With that field, we can supply sufficient amount of energy to the electrons so that they can come out of the metal surface. And the last one, but not the least, photoelectric emission. And this will be our next topic. Photoelectric emission, basically it's with the help of photons we can again eject out many electrons from the metal surface. Let's proceed on to photoelectric effect. Okay, alright. So photoelectric effect basically is a phenomena which gets us the idea that electrons behave as particles also. How they behave as particles? They possess energy, they possess momentum, and they interact with other particles. So definitely they behave as particles as well. And who are doing these things? Who is supplying the energy to electron? Photons. Photons are doing this thing. So photons are colliding. Photons carry energy, they carry momentum, they are colliding with the electrons and they are imparting the energy. That means the photons also possess particle nature. So photoelectric emission, in short, can be a clearer example to prove the particle nature of photons. Alright, so what is this experiment? We take a discharge tube, as mentioned here. This is a discharge tube. In this tube, we have two electrodes. Okay? We have two electrodes. One is connected to the positive terminal of the battery here, like this. Another one is connected to the negative terminal of the battery, like this. This one is anode, and this one here is cathode. Okay. Cathode is our target metal, or we can say it's our emitter metal basically. On this target metal we are going to strike the photons, which will do the photoelectric emission. Okay, now here we have applied a variable source so that I can adjust the voltage upon the requirement, as per the requirement to adjust with our experiment. So what do they say? There is a plate, the cathode plate, and this is the target metal. We are studying this thing. So we apply a high intensity light on it. Light falls in the form of photons. So many photons strike this cathode metal, which is our target metal. On this, photons with a high energy strike the metal surface. Now see, on the metal surface there are many free electrons, and in the starting I said that a particle can absorb photon and get its energy. So here the particles we are talking about are electrons. So electrons can get that energy from the photons. If they get energized, they will come out of the metal surface. So thus this is the photoelectric emission. Electron emission due to photons. That's your photoelectric emission. Now see, there are different aspects to verify ki are the electrons exactly or actually emitted from the metal surface or not, because we cannot see electrons. So how do we judge, or how do we verify? We verify it using the circuit parameters. Now tell me, electrons are charges, and when the charges move, they consider or they constitute current in the circuit. Correct or not? If the current is there, now there are devices which can measure the presence of that current. So with the presence of current, I can get the idea that there are some electrons flowing, and these electrons basically are coming from this metal. And how did it come from the metal? Because of photoelectric emission. Alright. So we say कि when the suitable light when the light of suitable frequency, suitable light falls on the photosensitive plate, the cathode plate, the emitter plate, okay, it's also called the emitter, the photoelectrons are emitted from it, which get accelerated towards the anode metal, which is in front of it, known as the collector plate. These electrons flow in the outer circuit through that emitter connected, and this results in photoelectric current. Due to this, the microemitter shows deflection and it measures the photoelectric current. This is the microemitter. Microemitter basically means it's an emitter which measures or which can measure very small amount of current. So let's carry forward and understand this experiment's observations. What did we observe? What did we observe based upon different parameters of photons? So we say कि at a particular wavelength, I see no photocurrent is produced even at higher intensity. What does it imply? Now, intensity basically tells us about the number of photons. Okay? In this chapter, in the photoelectric effect, if intensity is mentioned somewhere, we have to relate it with the number of photons and not just the energy. Check a number of photons, basically it's the number intensity they are talking. Now at a particular wavelength means at a particular energy of the photon. So in the starting we said that a photon must possess some minimum energy so that it can emit the electrons, and that minimum energy was called the work function, correct or not? Now at some particular wavelength, let's suppose it's a high wavelength, so the energy will be lesser, and if that energy is lesser than the work function, will it emit any electrons? No. So that's why there was no photocurrent, because no electrons were emitted. Okay. Now they are saying that below that particular wavelength, photocurrent was produced even at lower intensity. The emission of photocurrent from the metal surface when the light of suitable wavelength falls is called photoelectric effect. Now, the Einstein's photoelectric equation, let's write it here. It says that when there is this metal surface and the photons carrying this much energy strike on the metal surface, then electrons are emitted. This energy is supplied to the electrons, but to exit out of the metal surface, they must spend some energy with the metal, which is called work function of the metal. So some energy provided by these photons to the electrons is utilized by the work function, and there would be some energy left over. And this leftover energy becomes the residual kinetic energy of the ejected photoelectrons. Okay. Now some of those photoelectrons having that residual kinetic energy will further suffer collisions. Further they will collide with the other atoms in the metal lattice or with the other ejected photoelectrons, and they will lose that energy. But some of the lucky ones will get out of this crowd of ejected photoelectrons with the maximum possible kinetic energy, and we will call it Kmax. It did not suffer any collision. So considering that thing in mind, I can easily write that the energy supplied by the photon is transferred as some part is Kmax and some part is work function. So rearranging it, I can write the Kmax of ejected photoelectrons is equals to the energy of incoming photons h nu minus the work function phi of the metal. So here I got this Einstein's photoelectric equation, and we can have many formats of Einstein's photoelectric equation. I can convert this h nu as hc by lambda, because I saw that energy hc by lambda 12.12400 upon lambda in angstrom, so it's in electron volts. This work function is phi. Okay, and then some more formats we are going to discuss based upon the threshold frequency and the threshold wavelength. Okay, so how do we define this threshold wavelength and the threshold frequency? I can write the work function of the metal as hc by lambda naught, where what is lambda naught? Lambda naught is the threshold wavelength. What is threshold wavelength? It's the maximum wavelength, maximum allowed wavelength with which the incident radiation will or can perform photoelectric emission. If the radiation is above that, it cannot produce photoelectric emission. Okay, so that is your threshold wavelength. At threshold wavelength, the supplied energy will be equals to the work function, exactly matching the work function, so the residual kinetic energy of the photoelectrons will be 0. There won't be any kinetic energy left because all energy is utilized by the work function. So Einstein's photoelectric equation becomes the supplied wavelength hc naught, the k max minus the work function, k max will be 0. So we got the work function as hc by lambda here. Same way we can define the threshold frequency. Now what is threshold frequency? If the wavelength was maximum, this time the frequency has to be minimum. So threshold frequency is the minimum frequency with which incident radiation can produce photoelectric emission. It can possess minimum energy corresponding to the minimum frequency. Below that frequency, there won't be any photoelectric emission. Okay? So same concept I'll apply, exact same thing. So I'll write phi as h nu naught, and nu naught is the threshold frequency. Alright, let's move on further. The graph between the k max and the incident frequency. If I write the Einstein's photoelectric equation in a particular format, you guys see here k max h nu minus h nu naught, which is the work function. So this is on the y-axis and nu is on the x-axis. This is basically the graph of y is equals to mx plus c. Comparing it, c is your y-intercept, which is minus h nu naught. It's in the negative. I know it's below the x-axis, so it's negative. M is the slope. And can you guess what is the slope here? Slope is nothing but the coefficient of this frequency, which is the Planck's constant. So slope of the graph is h. Slope of the graph is h. And here you can see there won't be, now first of all, k max cannot be negative. So graph cannot exist below the x-axis. So the starting frequency at which the electric or the photoelectric emission happens is your nu naught, or the threshold frequency. Like this, we can draw the graph. So the graph is a straight line. Okay. In the same way, I can draw the graph of k max versus 1 by lambda. Okay. Versus lambda will be a hyperbola graph, but we have plotted it versus 1 by lambda. Okay. 1 by lambda will again be a straight line. Using this equation, k max is hc by lambda minus hc by lambda naught. Okay. Let's take up a question based upon the photoelectric emission. They are saying कि two radiations of photon energies 1 electron volt and 2.5 electron volts successively illuminate with photosensitive metallic surface of work function 0.5 eV, the ratio of maximum speed of the emitted photoelectrons. So we can first find the ratio of kinetic energy, the K max, and then we can get the speed. So let's write the K max. They are saying two radiations of photon energy is 1 electron volts. So the first one is 1 electron volts. The work function, same metal is used, so work function is 0.5. So K max in the first part comes out to be 0.5 eV. First scenario. Second scenario, K max will be equals to the incoming energy is 2.5 eV. So here I'll write 2.5 eV minus same metal, so same work function, again 0.5. So it becomes 2 eV. Now here if I write the ratio of kinetic energy in the first case to the kinetic energy in the second case, it will be 0.5 upon 2 or 1 by 4. Now I know that the kinetic energy ratio is equals to the ratio of square of the velocities, v1 square upon v2 square. So v1 upon v2 is equals to 1 upon 2. So 1 is to 2. This is how you can solve the problems using Einstein's photoelectric emission. Okay. Wave particle duality before proceeding to the dual nature of matter. So to exhibit dual nature, we must have some parameters which can decide or which can judge either of the nature or both of the nature. So they are saying ki which of the following optical phenomena can tell us about the dual nature of the light, either the wave nature or the particle nature. So reflection phenomena can tell wave nature as well as the particle nature. Both the wave and particle suffer reflection, correct? Refraction, again wave nature, particle nature. Refraction in the sense ki if it enters another medium, will it suffer a speed change? That we can easily say it can suffer a speed change. If it offers resistance to that particle's motion, it will suffer. Interference definitely is wave nature. Particle nature cannot show interference. So I can say interference is the sure test of wave nature of light. Diffraction, same way, diffraction also tells us about the wave nature. Particle nature doesn't perform or doesn't exhibit any diffraction. Polarization again is a wave aspect, only the wave nature. Nothing about particle nature here. While the last one, photoelectric effect, it has nothing to do with the wave nature. Only I need the energy, so it shows us the particle nature. Okay. Alright, effect of intensity on the photocurrent. Now see, intensity basically refers to the number of photons. So I can say intensity is proportional to number of photons per unit time, small n. Photocurrent consists of the emitted photoelectrons. That's correct. So I can say if I increase the intensity, the maximum photocurrent is going to increase because more number of photons are going to eject more electrons from the metal surface. That's absolutely right. So let's check out the graph. Here we have drawn the graph. Okay. Later on we'll compare all the three graphs. Right now let's make it here. On this we will plot photocurrent, and on this we will plot the applied voltage. Okay, here I have three different scenarios. What do these scenarios tell us? They are corresponding to three different intensities of light. I can easily see on the vertical axis the photocurrent is definitely different for all the three cases. I1 has the least saturation current. Saturation means the maximum photocurrent possible. So maximum photocurrent possible is in case of I3. That means it must have more number of photons per unit time. So I3 must be greater than I2 must be greater than I1. This is how we can compare. Okay, let's move on further. So photocurrent I versus intensity, that's what they are saying, it's directly proportional. So intensity and the photocurrent are going to be directly proportional. As the intensity of light increases, the number of photons incident per second increases, due to which the photoelectrons emitted per second also increase, hence the photocurrent increases. Alright. And here they are mentioning the saturation current. Okay, this is the collector plate voltage and this is little bit curved. Okay, they have not shown it properly, but it is little bit curved. Alright, fine. The next is about the stopping potential. Stopping potential is another aspect. Let's look after it. They are saying ki if the potential is reversed, now the emitter is connected to the positive terminal and the collector is connected to the negative terminal. Electrons being negatively charged, they are repelled by the collector plate. It's a straightforward concept. Okay, this is what they are saying. This was the target metal and now they have reversed the polarity of the battery. So this time the electric field in this region due to the battery will be in this direction, while the emitted electrons will be here. So they will be retarded due to this field, because electrons being negatively charged decelerate along the electric field. What do we see here? That will apply that reverse potential V0 in the reverse direction, so minus V0, such that the electric field is sufficient to stop the electrons with K max from reaching this anode metal, the previous anode metal, or I'll say the collector plate. This time it cannot be anode because I have reversed the polarity. Okay, so rather than that I'll call collector plate. This was the emitter plate or the target metal, and the electrons with K max are not able to reach here. So that's what the stopping potential is. So it is the minimum reverse potential at which the photocurrent stops. In the graph you can easily see the photocurrent is this yellow graph and it stops at this retarding or reverse potential, which is called your stopping potential. Okay. The effect of stopping potential on the photocurrent. So they say that the saturation current does not depend on the stopping potential, but definitely the K max is going to depend upon the stopping potential, or the stopping potential depends upon the K max. Okay. So number of photoelectrons emitted, they are proportional to intensity, that we know. We have seen that graph. For a given frequency, stopping potential is independent of the intensity. Alright, the effect of frequency on the stopping potential. So that we can easily guess. From the Einstein's photoelectric equation, K max is equals to h nu minus the work function. K max can be written as electronic charge into stopping potential's magnitude, and it will be equals to h nu minus phi. And if I rearrange it, V0 will be equals to h by E into nu minus phi by E. So here what you can see is stopping potential depends upon the frequency. Magnitude wise, here I am writing the magnitude, so you can easily tell which magnitude is more. This side the magnitude is more, so which frequency is going to be more? Nu 3. So nu 3 greater than nu 2 greater than nu 1, the magnitude wise. So they say maximum kinetic energy of photoelectrons vary with frequency, intensity being constant. The stopping potential is more negative for higher frequencies. More negative means more magnitude of the stopping potential. Okay. So stopping potential versus the frequency, we have just seen this graph. So again it will be a straight line graph. We easily know this thing. We have plotted it. Summary of the photoelectric emission. So we have seen the photocurrent is directly proportional to the intensity. First thing, the photocurrent versus the collector plate potential. So this is the graph. Then the dependency of intensity on the photocurrent or the saturation current. Then the last thing, the dependency of frequency on the stopping potential or the retarding potential. Now let's check out the problems which NEET has asked before. Let's quickly go through this problem. They are saying the photoelectric threshold wavelength of silver is given as 3250 10 to the power minus 10 means in angstrom. Threshold wavelength is 3250 angstrom. Okay. The velocity of the electrons ejected from the silver surface by ultraviolet light. So the incident radiation is this. Now incident radiation is lesser than the threshold wavelength, so that means it can perform photoelectric emission. Frequency should be higher than threshold frequency, wavelength should be lesser than threshold wavelength. Remember this point. Okay? So it is good to go. Wavelength has to be lesser. They have given the H as 4.14 into 10 to the power minus 15 eV. Okay, and C is 3 into 10 to the power 8. So they are asking what is the velocity of electron ejected from the silver surface. Okay, so I can write the K max first of all. K max is equals to Hc by lambda minus Hc by lambda naught. Okay. So here Hc can be written as 4.14 into 3, that is approximately 12, and if I use this data then it will be 1 2 and 1242 approximately. Okay, we wrote it 1240, but here I'll write 1242 approximately, and the lambda, and in the same way 1240 the lambda naught, and they both are in angstrom, so it will be good to go. I need not worry. And lambda, it's quite calculative, so I guess you guys can try it out. 1 by lambda is 2536 minus it is 3250. And you need to calculate it now. Okay, so calculate this part, you obtain the K max, and then what do? We write the K max as half mv square. So 12420 1 by 2536 minus 3250. Okay, angstrom, everything is balanced. This energy will come out to be in electron volts. Okay. Now mass of electron we know is 9.1 into 10 to the power minus 31, cross multiply and you will get the velocity. So if I check the options, the order of the velocity is either 10 to the power 4, it is again similar 10 to the power 4, or it is 10 to the power 6, or I can say it's 10 to the power 5, or here again it's kind of 10 to the power 5. So from that also you can verify the velocity. Okay, let's check another problem, a lesser calculation. The source of light is placed at a distance of 50 centimeters from a photocell. Okay, the stopping potential is found to be V naught. If the distance between the light source and the photocell is made 25 centimeters, the new stopping potential will be. Okay, so first of all, with this distance, I know that the intensity is going to change, but the energy of photon will not change. So if the energy of photon does not change, energy of photon does not change with the distance, only the intensity will change. So number intensity means number of photons falling per unit time will change. So here the photocurrent is going to change, but the stopping potential will not change. You can write it. Here the stopping potential doesn't change. Okay? Stopping potential doesn't change. What changes? We should write that also. Only the saturation current changes because of change in intensity. Because of change in intensity. Okay. So the answer is going to be V naught itself. It's not going to change. Next, in the photoelectric emission process from a metal of work function 1.8 eV, the kinetic energy of the most energetic photoelectrons is 0.5 eV. The corresponding stopping potential is. Now it's a very nice and sweet problem, straightforward. Just apply Einstein's photoelectric equation, K max h nu minus the work function. They have said the work function is 1.8, the K max is 0.5 electron volts, this is h nu here, and this becomes 1.8 eV. Okay. So here the incident frequency and the energy will be 0.5 plus 1.8 eV. So we can get the incident energy, and they were asking the stopping potential. So stopping potential will be simply with the K max. K max will be EV naught. Okay. So the K max is 0.5 and the incident energy will be your 2.3 eV, while the stopping potential will be 0.5 eV upon E. So V naught comes out to be 0.5 volts. So here our answer is going to be 0.5 volts. Now I just solved the upper part to show you ki what options do they mean, what does the options represent here. So basically I have found the h nu using the Einstein's photoelectric equation. I have found the incident energy 2.3. They were not asking about this, they were asking about the stopping potential. Stopping potential depends upon the incident energy, but it is equal to the K max upon the electronic charge. So remember that thing. So answer will be 0.5. Great problem. Alright, now let's talk about something related to the momentum of the photons and how do we talk about the radiation pressure. So basically what happens if some particle falls over its surface and doesn't rebound back, it gets absorbed or it gets attached. So the change in momentum will be the initial momentum itself. That's it. If it rebounds back again in the same direction, then the change in momentum is twice 2 mv. While if it rebounds back and it's coming at an angle, then the change in momentum is 2 mv cos theta. Accordingly, we get the radiation pressure. Radiation pressure is basically the pressure exerted by the incoming radiation on the target metal surface. Because if something is continuously striking on a surface, they are exerting force. Force per unit area, average force per unit area will result in the pressure, radiation pressure. Okay. So first scenario, in case of completely absorbed radiation, your radiation pressure will be F by A, and if I write it properly, it comes out to be I by C. Just remember it. Okay. Next, complete absorption we have done. In case of complete radiation, sorry, complete reflection, in case of complete reflection, I know the change in momentum will be 2 mv, so the radiation pressure is 2I by c. Alright, now comes your matter waves. So de Broglie's hypothesis says just like photons, the momentum of any particle, the matter, if they have momentum, then it can be related with their de Broglie wavelength using this formula. So P is the momentum of the particles of matter. Lambda here is their de Broglie wavelength. De Broglie wavelength. Okay, check it out. The light of wavelength lambda in intensity I is incident normally on the surface. If the reflection coefficient is R, okay, the reflection coefficient is R, the pressure exerted by the light on the surface. Now see, here the change in momentum will be in terms of R. If it was completely reflected, then the change in momentum was 2 nv, so radiation pressure was 2I by c. But if R is something else, then the radiation pressure will be 1 plus R into I by c. Okay, so it will be 1 plus R. Okay, matter waves, now they are just relating your de Broglie wavelength lambda with the momentum. Momentum is mv. So in case of de Broglie wavelength, if I have the kinetic energy, momentum and kinetic energy are related like this. So I get the de Broglie wavelength lambda as h upon under root 2m kinetic energy. Okay. Alright, this is how we can get the de Broglie wavelength for different particles, let alone the electron here, the most important. The de Broglie wavelength is directly related as 12.27 angstrom upon the applied voltage. Applied voltage, why? Because applied voltage can give you the required kinetic energy. Kinetic energy will be E into the applied voltage. So using that, I got the de Broglie wavelength. Okay. The observation here, this thing, for the electrons, if the V is 50 volts, so they are getting the wavelength as 0.167. Okay, the properties of matter waves. Matter waves are related to the moving particles and independent of the charge of the particle, correct? The phase velocity of the matter waves can be greater than the speed of light. Interesting point. The wave and the particle nature of moving bodies are mutually exclusive. They can never be observed at the same time. So at times it will show wave nature, at other times it will show particle nature. The matter waves represent the probability of finding a particle in the space. In ordinary situation, de Broglie wavelength is very small and the matter waves can be ignored. Alright. Just an example of a baseball of mass 138 grams and the electron of mass 9 into 10 to the minus 31. Speed of baseball is this and the electron speed is that. So here the de Broglie wavelength is very small, 10 to the power minus 34, while there the de Broglie wavelength for the electron is 10 to the power minus 9. Okay, alright. Let's take a quick question of de Broglie wavelength. Which of the following is true about the de Broglie wavelength? When wavelength is very less as compared to the dimension of the object, wave behavior is observed. When the wavelength is comparable, then the wave nature is observed. De Broglie wavelength are electromagnetic in nature, de Broglie wavelength are longitudinal. So if it is comparable, then we can observe the dual nature of matter. Alright, so that's it for today. That was your photoelectric effect and the dual nature. Thank you.